Hey, everybody. So we're going to use the notion of the linear approximation that we talked about in the previous video to talk about something called differentials, and we'll use them to investigate one instance or two instances of error out there. So we'll say more about them shortly. Here we have a picture that is very familiar at this point. I've got a function f, and I have its tangent line at the point a, f of a, which we're now just giving this name L of x, the linearization of f at a, right? So let's put that in. L of x is the linearization of f of x at a, okay? But this is just to say it's the tangent line, and we use it as an approximation to f. That's really all we mean by this linearization. We're taking the tangent line and using it as an approximation to f near a, right? So that was one of our big, so let's write a couple things down. Remember, L of x is f of a plus f prime of a times x minus a. That's our tangent line formula manipulated slightly. Or equation, the way we've typically been writing it. And then we have this notion that f of x is approximately L of x, or f of a plus f prime of a times x minus a near a, right? That was all from the previous work, okay? So now we're gonna consider this approximation a little more closely. Imagine using this approximation. Now I'm going to exaggerate this picture a little bit. It feels like A is not quite below. Oh, I guess that is below. I don't know why I need to erase that. So there's A. And let's imagine we put in a value near A. So I'm going to write that as A plus dx, right? Dx here is just meaning some small amount of input, right? So that makes this interval here, the width of that interval is dx, right? This is equivalent to delta x, right? When we have two different x values, and so we can use both notations, but we'll see why we're going to use dx in a minute. Because when we get to the y values, there's going to be a difference between delta x and dx that we're going to examine, okay? So what we can say, so let's label some things on our graph. This point here, this is going to be, the height of this is going to be f of a plus dx, right? That's the output value of the function at this input a plus dx. And over here, this is the value L of a plus dx. Okay, now I've exaggerated my picture for the sake of illustration here. There's a pretty big gap between these, right? We really would be doing this at this place where they're very close to each other. So this, I'm stretching everything out, but really imagine trying to draw all this, you know, just very, very small units away from this place where the tangent line hits the actual function, okay? So because we're thinking of dx as something small, we're certainly near a. So f of a plus dx should be approximately equal to what I have on the right here, f of a plus f prime of a times, and we're evaluating this not at x, we're putting in the value a plus dx minus a, right? And if we work that out, we get a plus dx is approximately equal to f of a plus f prime of a dx, right? So remember a little bit about what we said yesterday. This I'm thinking of as kind of like a speed relative to how much x we change, and we're multiplying that by how much x we change. That's telling us how much y changes, okay? And then this is where we started. So we have our starting point plus how much we change to get our finishing point. Of course, there's an approximation in here. They're not precisely the same, but they're close to each other. We're going to manipulate this a little more. I'm going to subtract f of a on both sides. And so I have f of a plus dx minus f of a is going to be approximately equal to f prime of a dx. Now let's examine this more closely, right? So this, let's go to blue. This again is how far we've traveled in the y direction using the derivative at the point A as our speed, right? And we know that the speed of the function, so I'm using speed here a little bit improperly. What I mean is the rate at which y changes or f changes as the input changes. We're using that rate at A to represent the rate as we move away from A. But of course, looking at the graph of f, the rate at which the output changes doesn't stay the same as we have different inputs, right? The output is changing less, for instance, as I move to the right of A. You can see the graph getting flatter. So change in an input of X doesn't yield as much change in output, but it's something approximating this, right? On the left-hand side, we have precisely how much the function changes, right? This f of a plus dx minus f of a represents precisely this distance. If I look at the height, this height here is f of a. So this horizontal distance from that point on the graph above a plus d of x down to this horizontal line that's at the same height of f of a, this whole distance right here, this is precisely f of a plus dx minus f of a, right? This is something we've used before. We're going to call this delta x. Oh, sorry, delta y. It's our change in output, excuse me, delta y. So let's rewrite this equation here, or this approximation is delta y is approximately f prime of a dx, right? So what I'm saying here is the amount of change in the function is very similar to the amount of change, the actual amount of change in the function delta y is approximately how much change we would get if we kept changing in the same way as we did at a for an interval of dx. This over here also has a geometric interpretation on this graph. It's going to get messy here. Let's pick a ridiculous color to draw on top of all of them. Let's take a light radioactive green. This distance from here to here, that green distance is f prime of a dx, right? Because we're taking, if we take how far this interval is and multiply it by that speed, we get how much change we get in this line, right? Because that line, that linear approximation, it's a line and it's changing at a rate of its slope, and this f prime of a is its slope. And if you move the slope by dx, sorry, if you move the input by dx, you'll move the output by dx times the slope, which is what we have here. So this height, this change in height from this, the value of the linear approximation at a to the value of the linear approximation at a plus dx is what's on the right. So all this statement says is the change in the function over an interval near a is approximately the same as the change in the linear approximation, which is what we've already been saying. We're really just adding some notation here, right? That was the whole point of the linear approximation. So let's add one more piece of notation to this. We give this expression here a symbol, and that symbol is dy. So this big green change here that I've now overlaid with black, we call dy, right? So we have a difference between delta y and dy. Delta y is how much the function actually changed. Dy is how much the linear approximation or the tangent line changes over the same interval, right? The interval in this case is dx, right? So this dy is equal to f prime of a dx, right? You might see this written as dy is equal to dy dx, right? And the meaning is the same. And it looks like a very simple algebra problem. If we think of these dy's and dx's as the same thing, we started with dy over dx equals dy dx, and we multiplied both sides by dx, right? But it's telling us something, right? Even though it's algebraically looks fairly straightforward, it's telling us something important. It's telling us that we can measure an approximation to how the function changes by looking at how the tangent line or the linear approximation changes. Now, let's say a couple more things about this. Dy is equal to, so I'm going to change this instead of f prime of a, I'm going to say at x, only because now I'm thinking of this more generally, right? Each time we build this at a certain spot, then we have an a, but when we have it more generally, when we haven't picked a specific spot, we're going to represent that with our x. We are defining, we have three variables at play here. Dy is our dependent variable. In other words, it's a function of the other. Usually we have another variable, but we have two variables that dy depends on. The two independent variables are x and dx. Oops, dependent variables. Okay, so what do I mean by this? Well, usually when we have y as a function of x, we mean if we change x, y changes, right? We get a different output. Every change in x yields a change in y. But now we have two things that y depends on. If I change x but keep dx the same, then y will change. Or if I change dx but keep x the same, dy will change. Or if I change both of them, y will change. Let's see this a little more clearly. What each does. So if this is my f of x, if I pick a point, let's say here, call this a, right? So there's a tangent line that I could draw here. I'll try to eyeball it, something like this, right? The choice of a, that's the x part of this. I'm choosing a value for x. The choice of x tells me how big f prime of x is going to be. Look at this, at this value a, f prime of x is pretty small, right? So dy equals f prime of a dx. So if I move over to a plus dx, right? dy is how high now the line has gone. It hasn't gone very much, right? There's a small change there. On the other hand, if I choose a point like B, call this B, so this is B, f of B, I guess I should be more careful, A, f of A. This is going to be B, f of B. And imagine the tangent line here. If I move over by approximately the same amount, right? So this amount is our dx. So let's say I do the same dx over here, just eyeballing it. There's dx. How high does that line go? The change, remember the height and the change in that blue line as I move to the right by dx is dy is huge there. So here I've kept dx the same, but changed the input x, and I get a very different dy. So depending on where we're doing this, what x value we're doing it at, we get very different values. On the other hand, I can also change dy. If instead of moving over quite so far, maybe I only move this far, then this smaller line would represent the dy. And same thing here, if I only move this far, dy becomes smaller. So changing either of these variables, x and dx, changes dy. This is something that we'll examine more in later courses where we have functions of more than one variable. But all we need to, we're thinking of this more intuitively. It's another way to say it is just functions are changing at different rates at different places. So depending on which place we use the rate of to approximate, we get different results. And then also how big an interval we make our approximation over. The further away you get from where you made your approximation, things get worse. So that one's changing x, one's changing dx. Okay, let's move on and see how we can use these in measuring certain kinds of error or approximating certain kinds of error. So let's imagine this scenario that for some reason we need to measure a tiny little square of something. So suppose I measure some material, a square of some material to have side S equals 1.1 centimeters, right? That's what I measure it to be. And actually though, let's say truthfully, I mismeasured it. Maybe I have a bad ruler, maybe whatever my method was wasn't very good, and the actual side length is 1 centimeter. Well, I can take this side length and pop it into an area function. And then it's very clear, well, let's just write it out. The area function, of course, is just A of S is S squared. The true area would be 1 centimeter squared. But my measured area is going to be 1.21 centimeters squared. Right, so I made an error. That error in measurement propagated into the error in the result of whatever I was doing with that measurement. In this case, computing the area of this little square, right? So we call this propagated error. This kind of error that moves from a measurement into whatever it is you're doing with that measurement, okay? Now, we can use differentials to approximate these kinds of propagated errors. So let's examine that idea. So if we're going to measure something, right, whatever it is we're measuring has some true value. I'm going to call the true value A, right? In the case of this example, the true value was 1 centimeter. But when we measure it, we might get something a little bit different. I'll call that A plus dx, right? So in my case, I measured it to be 1.1, the dx was 1/10 of a centimeter, right? Again, errors in measurements are pretty much guaranteed. Our tools have a limited amount of precision. We're prone to make errors. All kinds of things can go wrong when you're making measurements. So there's almost always going to be some amount of error, okay? The error is the difference between the error at the end, the propagated error, right? So I made 1/10 of a centimeter error in measurement here, but I ended up with 0.21 centimeters squared error in difference from the actual area, right? So that's the area after we do what we're doing with our measurement. And that's going to be, so F is the function. In this case, it's, I did one with the area function, but maybe you're measuring something and you're going to find it's, do something with its mass or its volume or who knows what you're going to do with it. But the error is just going to be delta y, the difference between what you got and what you should have gotten were you able to measure the true value. Now recall, delta y is approximately dy, which is equal to f prime of a dx, right? That's what we just did with these differentials. The problem is, right, in my example, somehow I knew the actual side of the square was 1 centimeter, right? Well, why would I be measuring it if I actually knew? In a typical example, we won't know that. We'll do an example in a second like that. But we don't know what the actual one is. So we can't know what A is, right? If I didn't know that this was 1 centimeter and I measured it to be 1.1 centimeters, I might guess that I made some amount of error, but I don't know if my error is to measure it too long or too short and by how much. So I wouldn't actually know that. So we won't know what A is. But we're only trying to approximate things. So we can approximate this further by saying dy is approximately f prime of a plus dx. That's our measured value times the differential dx. Okay, so there's a lot of notation here. Let's see this in practice. So for this, we know in this square example exactly what the area is, but I'm going to pretend for a second that I don't know this. Right? I'm going to pretend I don't know this. I don't know what the actual side is, and I don't know what it is. But let's say I wanted to approximate how bad my measurement might be, or my calculation of the area might be. Well, dA is going to be a prime of, so I'm just copying this instead of dy, I've got dA, then f prime at the measured value, 1.1, times dx. dx is how different is the measured value from the true value. Now, here's where this example gets tricky as well. How do we know how different it is? Well, let's just say our measurement device maybe has a known error. The machine that produced the rulers I have tells me that the measurements on it can be up to 1/10 of a centimeter off. So I can take that to be my dx. Okay, well, what's a prime of 1.1? Well, dA, a prime is going to be 2s. So that's going to be 2 times 1.1 times 0.1. This is going to be 2.2 times 0.1. And so we get an approximation for dA to be 0.22. Right? Notice in our example, when we knew the true value, the actual error was 0.21. So our approximation is not too bad here. So if we were trying to guess how bad, how much the area could be off by, this would give us a pretty good approximation of that. Let's do an example that's a little bit more realistic now that we have put the pieces in place. Let's just say that an engineer has built some kind of dome, maybe some kind of sports dome or something like that. And they measure the radius of a dome, right? And so here, this is a dome, I mean a half sphere, so precisely half of a sphere, to be 31 meters. Accurate to the nearest centimeter, or 0.01 meters, right? So they have a tool, maybe some kind of laser sight or something like that, and they know that this thing is going to be accurate down to the centimeter. So we don't know the true radius of this sphere, or half sphere, but we know that the process by which we took the measurement could lead to an error of up to an entire centimeter, or 1/100th of a meter, okay? We want to know, what does that mean? Maybe we're trying to estimate, we're installing the air circulation system, and we want to know the volume of air that's going to be inside this dome. So we want to estimate the error we might have in the volume, right? Is it a big enough error that we have to worry about it when we're installing this system? Well, let's look at let's use differentials to do this. We're going to start with the volume of a half sphere. So it's going to be a function of the radius. It's the volume of a sphere is 4/3 pi r cubed. So this is going to be half of that, or 2/3 pi r cubed. That's our volume formula. So we can write that, we can take the derivative, dv dr is going to be 2 pi r squared, and we're going to write this in the form of differentials. Right? The change in the volume, right, or at least the linear approximation to the volume, is equal to the derivative of the volume formula, 2 pi r squared, times the change in the input r. Okay. in terms of our error, what we can say is dv is going to be 2 pi. So we're going to use the measured value of the radius, 31 meters squared. dr is the error, and we're going to use what we know about our tool, that it might have up to 0.01 meters of error as our error, as our dr. Okay, we multiply this and we get 60 to the nearest to 2 decimal places, 60.38. And our units, notice we have meters squared and meters, so we have meters cubed, which is good. This is the error in volume. It should have units of volume. And so if our, this is really a worst case scenario, right? Our measurement might have been better than this, but our error could be up to 60.38 meters cubed, right? In other words, we don't know which direction this error is in. So this dv, right, this is not, I want to be careful, this is not this is not the volume, this is how much the volume might be off by. And dv should be no larger than 6.38 meters cubed, but it could also be in the negative direction. Right, so whatever volume we get with 31 meters cubed, right, that would be this 2/3 pi times 31 cubed. This is where you might have a plus or minus 60 point, we'd probably say 60.4 meters cubed, right? Plus or minus that amount by this error estimate. It's telling us how bad things could be. All right, now let's look at these two examples. In the first example, example 1, we were off by our error, or our error estimate was 0.22 centimeters squared. In example 2, our error is 60.38 meters cubed, the size of our error, right? It can, in this case, could go in both directions. Now, looking at these two errors, it's really difficult to compare them. Right, they're different units. How do you compare area to volume, right? Certainly, I think we all feel like 60 meters cubed is somehow bigger than centimeters squared, but that's really not an accurate thing to say. Area and volume are just not. What's bigger, a football field or a half a mile? Well, a half a mile is longer, but it's only in one dimension, and a football field is a plane in 2 dimensions. So how do you say? You can't say which one's bigger, right? Same thing here. And so it's hard to say which of these errors is worse, right? But one thing we can do is we can compare them to what it was they were trying to measure. Okay, so since, right, in that kind of phony example I gave first, I somehow knew the actual area of the centimeter, this perfectly 1 centimeter square material, we won't usually know the actual value, but we can compare it to, we're approximating things here, and so we can compare it to what we got in our measured value. And we call this the relative error, okay? So the relative error, we're going to compare, oops. We're going to compare the error to the measured value. But what we're really going to compare is the approximations we have. So for instance, with error 1, the square, we can say the relative error is going to be dA over our measured value of A. So if you look back, our dA was 0.22, right? dA was 0.22. And our measured value of the area was 1.21. Whoops. 1.21. And this works out to be rounded to 3 decimal places, 0.182. This tells us what proportion of the measured value the error takes up. This is a pretty big proportion, right? This is, we can turn this into a percentage error. This is 18.2%, right? I like the decimal, we just see it's a 0.182 of the measured quantity can be taken up by error. Error 2, even though it's much bigger, we're going to look at dV over V. So dV, we got to be 60.38. Oh, and I forgot to do units on that last one. Let's look at the units in this one. We have meters cubed. V is going to be our measured value for V. So this is going to be V of 31. In other words, we're doing 2/3 pi times 31 cubed. The units here are also going to be meters cubed. And so we get a number that has no units. The units cancel. So you can work this out to be, and we get 0.000968 or 0.0968%, right? So even though this is a larger number and somehow volume seems bigger than area, it's relative to what it was trying to measure. This is a much smaller error, right? Less than 1%, whereas the other one is close to 20%. It's off by about 1/5, whereas this is a nearly imperceptible difference in the true value and the error value, even assuming the worst case scenario that our laser guided measurement device was off by its maximum offness. Okay, so we call this the relative error. It tells us how bad the error is relative to what we were trying to measure, right? If I'm trying to draw a 1-inch line and I'm off by 1/2 inch, that's a pretty bad error. And if I'm trying to take a piece of chalk and drag it down Rainier Avenue until I get a line that's exactly 1 mile long, and I'm off by 1/2 inch, people would be amazed, right? And so the same 1/2 inch error, it has to be seen relative to what it is that you're measuring. And so we have this notion of the relative error, and that's just one of our uses of differentials. Okay, that's it for this one. Thanks, everybody. I will see you next time.